All right. What is up, everybody? My name is Alex Chisholm, co-founder of Data Query. Thank you for joining us today. This is our first of 7 workshops that we're going to be working on, focusing on machine learning, supervised machine learning in Python. This is the first one. We're going to be making predictions with linear regression techniques. And to do that, I'm helped out by my co-founder, David Sponsor. David, you want to say hello?
Hi, everyone. I'm glad everyone could make it, and I'm really excited to get coding in Python today. It's a very applied workshop. It's going to be really fun.
Yeah, and we are running live on YouTube right now, as well as in this Zoom meeting. So if you have any questions along the way at any point, drop them in the chat box on either platform, and we'll be able to sort of keep up with you, hopefully in real time. What we wanted to do this for is in some ways demystify what machine learning is, what it isn't, and how it can be applied to solve real problems, in your day-to-day work for either yourself personally or for your organization. And I think I'm really curious about how we even define what machine learning is today. And I think if you do a Google search for it, you're going to find a lot of different ways that people kind of explain what it is. But I'm curious for you, David, a professional full-time data scientist, how would you do that human language explanation of machine learning?
I like to just really keep it simple. And the definition I use is just algorithms that do automatic pattern recognition from data. And I think everyone can kind of understand that. When you're given a data set, you usually have to manually go through it. And then you start seeing patterns and trends. If it's a customer data set, maybe certain customers, if they come to your website at a certain hour, they tend to purchase a lot more of your product, right? So that's a pattern in the data. So it's just a set of algorithms where you don't have to write any rules kind of explicitly, and it will just find those patterns in the data by themselves. They're designed to do that. And that's really all that machine learning is. And many people kind of think that it's more of a general AI type of capability when you say machine learning. So, hey, these algorithms can think for themselves and they have consciousness and things like that. But that's not really what's going on. They just are combing through data, they find patterns, and they find the best way to separate different outcomes based on those patterns using mathematics. That's all that's going on.
When you say without written or explicit instructions, how does that differ than coding in the past or programs being written in the past? And why is machine learning so different than the old paradigm?
Yeah, so in the past, people would write these rules explicitly. So they would look at the data manually, they would discover patterns, and then they would code these rules. So maybe if you had a website, you would code a rule that would say, if somebody goes to this page and they stay for exactly 24 seconds, offer them a discount, because most people that do that aren't going to purchase, right? So you code that rule and it stays the same, the whole time. And every time you find a new trend, you have to update those list of rules you have. And so that's the old way of doing things. But with machine learning, you give the algorithm a data set with all of the customer behaviors and labeled outcomes, whether they purchased or not, and it will give you those rules. So that's the difference. It generates them automatically for you based on the patterns it discovers when it's trying to separate the people who maybe purchase or don't purchase. So it's kind of an inverted way to do it, right? You don't come up with rules, you come up with data and you are given rules kind of automatically, which is amazing.
And we hear a lot about different types of machine learning: supervised, unsupervised, reinforced. This workshop is going to be based primarily on supervised machine learning as we go through. Can you give that distinction between maybe those two, the big groups, the supervised or the unsupervised, and where they have differences?
Yeah, so for the supervised learning algorithms, that is when you have data that has labeled outcomes. So they're usually called a target column or an outcome column. So if we go back to that example about looking at customers, right, you would have a data set with all the customer data and behaviors, and then you have that label associated with each person, whether they purchased or they didn't, or maybe the amount that their purchase was, if you're trying to predict how much they will spend. So that's the key in supervised learning. There's a known answer associated with all of the different features in your data set. And then in unsupervised learning, you still have the same data set. Maybe you have customer data, but you don't have an outcome that you're necessarily predicting. There is no label associated with the data. So these types of algorithms are used for finding structure in your data set. And maybe if you've ever heard of customer segmentation models, it finds customers that behave in a similar way based off of data. So that is kind of ambiguous there, right? When you say when they behave similarly. So there's no kind of target outcome there. You're just grouping people based on when they decide to do things, and maybe they kind of clump together based on activity. But that's what those type of algorithms will, when you give them a data set, you get these characteristics of that data set that you would have maybe missed, yourself if you were combing through them by yourself.
Yeah. We have a question coming in already saying, what is better, supervised or unsupervised? And it's not necessarily going to be a case of which is better. What is the problem you're facing, and kind of what you're trying to get from implementing one of these solutions?
Yes, and usually it depends on what data you have. So when you're working out in the industry, getting data can be very expensive. You might have to conduct surveys to get those true labels for people. And there's all sorts of kind of factors that play into that. So it really depends on what data you have, and it depends on the goal you are, trying to achieve. So if you're trying to segment your customers and you don't really know how they behave, that's naturally a unsupervised learning algorithm. Regression won't help you there because you don't have an outcome for your customers because you don't know. So you can't really do that.
And that's what's going to make supervised learning here give us that unique prediction that we're going to be able to get from a model. Mm-hmm. And this is what everybody, or most people that are using machine learning, are looking for. We're looking at all this data, we're going to do something to it, we're going to apply some algorithms to it, and it should spit out something that's going to say, based upon the data we have, this is the most likely outcome that we can kind of think of right now. Mm-hmm. And the real business question is going to be, when you get that spit out, when your machine learning algorithm tells you that the person that just signed onto your site is most likely to convert if he goes through this page sequence on the site, what are you going to do as a business to make that predictive model's decision useful for you? Mm-hmm. And I know you talk a lot about business relevance in machine learning. And in some ways, I think data science and machine learning specifically are still this great big black box where you see executives thinking, well, we have all this data, let's just throw data science at it, let's throw machine learning at it, and obviously we're going to get some profit or some value coming out of it. So in your experience, before we get into some code, where is the most important position to start thinking, how am I going to use a potential prediction that could be generated through machine learning?
Yeah, so I mean, the biggest consideration is you have to really think about your kind of technical infrastructure you have at wherever you're working at, or if you have your own website. Because these things can get very complicated. So if in real time you have this model that based on a person's behavior on your website will spit out a prediction, you're going to want to take that and take actions in real time. So you have to have a way to be able to send that data almost in real time for potentially thousands of people on your website, and have kind of rules associated with each one. If something's very likely, maybe try to send them to this page or try to get them to click this button. And those things can be incredibly challenging to do. So that's called putting a model into production, when you make it available as a service, as an API, and then either a business unit or software uses it as input. So it's usually a lot more difficult than most people think to get that to work well. So that would be my number one consideration. And I always like to tell people, just remember, if you fit a model and it's just on your laptop, that's not really good to anybody, right? Now we're in the age where people have to know how to use the results of your model so you can drive impact at a company. Right. So that's usually the hardest part, is to figure out, what is my model going to predict? How is it going to drive success? And then how are people going to be able to use it easily, right? Non-technical people. So those are the key things you really have to think about before you get started. Yeah.
Yeah. And for the rest of the time tonight, we're going to be going through a notebook, a Python notebook, which we'll share with everybody who's attending tonight, along with the data sets that we're going to be using. But we're going to really just build up a sequential order for doing machine learning with linear regression. And I think that's the most important blocker that some people have. So they're the prerequisites for this workshop that we're running for the next several months on the first Saturday of each month. Are having basics with Python. But once you have sort of the basic fundamental skills within Python, you'll be able to go through and sort of just build up these different equations, call in these different libraries and packages, which we're going to talk about. That is going to give you a blueprint from how to run from looking and exploring your data to coming up with that final prediction, and then evaluating its accuracy and its performance ultimately. And I think today earlier I was doing a puzzle with my kid. And typically, I don't know how you approach puzzles, but your puzzle usually looks like this, right? It's usually a square. And the way I do it, I always get the pieces that have the straight lines and I dump them in a pile. And then I put everything else in the middle and maybe I color code and segment those out. Today's puzzle was in the shape of a horse head with no straight lines on the side. And then it had some pieces that were animal shaped in the middle. And at first I just stared at it like, what am I going to do with this? Like I have no system in place to even move forward. And it was really hard. And it took a lot of thinking to find out that, I should start with the pieces that are shaped like an animal and find things around them and then find the next animal nearby. So because I lacked that blueprint, I was sort of paralyzed and I couldn't do anything. We hope that this session is going to give you some kind of blueprint for attacking linear regression problems using Python.
Yeah.
So David, if you want to go ahead and share your screen, we can start talking through the code that you've got.
Great. And as Alex mentioned, we're going to share the link with everybody so you can just get into this notebook environment and you'll be able to run these cells as well, with me. That would be really good, I think. And so we're using this product. It's called Deepnote, and I'm a big fan of it because you can have a project where you can upload data. You can have Jupyter notebooks, as they're called, and it's just one kind of enclosed coding environment. And it's very easy to share with people, and they can just execute your code and everything will work. So they don't have to worry about software setup or any of the typical hurdles that beginners kind of face. It's just setting up your computing environment. It's very difficult. So here in our environment, we have a couple files. So we have our data file that's going to have all the data we have in this whole series. And then we have these notebooks. So for now, we just have the first one, linear regression. But throughout this series, this is where we're going to be adding all of these notebooks as we go along, going through all the different steps. Okay. So this first cell here, all this does, and if you want to run it, you just click the play button here on the notebook. This is going to set up our computing environment. It loads all of the libraries that we're going to be using and kind of sets up printing, for this notebook. And I wanted to call this out because this is the standard usually in the industry. So you want to put, if you're bringing in any outside packages like Scikit-learn or Pandas, you really want to put this at the very beginning of your notebook. So all the users will see exactly what is being loaded in, and there's no confusion anywhere down the line. So what we're going to be using today is Pandas. This is a data analysis, data manipulation library, a very famous one from Pandas or Python. And then for data visualization, we're mainly going to be working with this package called Seaborn. And it is just great because it makes it extremely easy to make some really awesome graphics, which I'll show you that are going to be very helpful for linear regression. And then finally, for the machine learning part, we're going to be using Scikit-learn. So the alias in Python is sklearn. That's the package name. And so here I'm just importing the functions I'm going to be using for the various steps as we fit these models. And then the last package, which I'm a big fan of, is called Yellow Brick. And this has great helper functions for you to evaluate your model performance. It's kind of really easy to visualize how well your model is doing. And we'll get to that towards the end of this webinar.
For
All
some
right, so
people, it might seem like these packages are kind of random. Like how, David, did you find out over time the ones that you prefer to use for a process like this?
yeah, I mean, this used to be confusing back in the day when these things were coming out back in 2012 or so. But now in data science, it's really just become the data science technology stack, right? That everybody always uses. It's always pandas. You have NumPy for numeric computations, and then for visualization, MATLAB or Seaborn, and then for machine learning, sklearn, scikit-learn. That's kind of the standard. And the one, I guess, the way I picked up on that was when I downloaded this package or software called Anaconda, and that downloads a whole entire Python environment to you. And these are the core packages that are available, always in that environment. And same thing with Deepnote. Even if you open up a brand new notebook and you don't import anything at all, these packages are already pre-installed in Deepnote as well, because they're just so standard now. But really, it's just blogs and,
Yeah. Speaking of Deepnote, another question coming in about the cost of Deepnote. Are they going to be able to run this stuff for free, or are they going to have to pay some subscription?
No, so everybody gets 750 hours of computing time for free
Not
a
bad.
month.
Not bad.
So yeah, you should have no problems. The only, and if you do want to get a subscription, I believe they're very affordable. I think it's only $8 a month, and that gives you more advanced features. You can have collaborators, you can have people join, your notebook environment. You can have GitHub integration, all sorts of, cool other features. But just for free, this thing is just a powerhouse, and I recommend it to everybody, all my students. It's really good.
Cool.
All right, so that's the setup. And again, if you're new to this, if this is confusing about these packages, don't worry about it too much at this point. We'll get to that a little bit later, some more detail. We'll have more webinars probably in the future on Pandas and how great it is. So just as long as it works for you today, that's all that matters. All right, so Alex mentioned, that it's important to have a process every time you try to, tackle, any problem. But for data science, luckily for us, there is an industry standard where it's usually the same exact steps that are followed for every single project. So it makes it easy to ensure that your project is successful. All you really have to do is just follow these steps and make sure to do them in order. And it's going to help you out a lot. And so this methodology, it was originally developed in the 1980s. It's known as CRISP-DM. So it's a process for what they call data mining back then. So this is before, the term data science was, being used. I think it was data mining first iteration of that. And it's got these 6 really important steps that we're going to go through actually with our project here. So we're not just going to fit only a regression model and show that to you. We're going to actually have a real business case, business problem we're going to walk through and show you how you would solve this with linear regression. So the first step, let's just go through these kind of one by one, is business understanding. And I think that this is the most important step in any data science project, no matter where you are, which company you're at. This is always the most important thing. So it's important to, as the data scientist, not just to jump into coding and building fancy models just because it's really exciting, right? That's what a lot of people like to do. But it's really important to understand how the business works and the people that you're building the model for, what do they view as success? Because if you don't know that, you won't be able to say whether your project was a success or not, right? And you never want to be in that situation if you're at work where you spend a month on a project and then it's kind of, you're not sure if it's successful or not, or people don't really like what you built because it's not what they were expecting to get. So you really got to avoid that happening. So for us, we're going to work on a sample business problem here where we have a data set that has a bunch of attributes of wine. So we're working with a wine producer, a pretty large one. So they make about 200,000 bottles of red and white wine every year. And their goal is to use machine learning so that they can predict the quality of their wine bottles, right, that are being produced, their wine. And they have a lot of sensors in their production process. So it measures a lot of things along the way as the wine is being developed. So things like alcohol content and pH and sulfites and all sorts of chemical measurements are coming out of their business. And so what they've done is that they've collected at random, they picked 1,500 bottles of wine over the last 2 years that came out of production. And then for each one, they had 5 different experts, taste them and then rate the quality of that wine on a scale of 1 to 10. So that's the data set that they have. And they would like to see if we could use it for predicting the quality of new wine bottles, right? Or new wine, not bottles, wine that's being produced. So before we continue, it would be important to talk to people in the business and ask them, what is success? I mean, how accurate do you need those predictions to be? So if we're on a scale of 1 to 10, is it okay if, the prediction error is plus or minus 2 points? Does that not matter? Because that might be the case. Maybe they're just interested in, I just have to find bottles of wine that maybe fall below 5 on that scale. So I could make sure to not include them in production because they're very bad quality, right? So that's very different from this success criteria here, where let's say we talk to the owners and they said, no, the predictions need to be within 0.5, quality points for the true quality of that wine. And it's very important to them because they sell their finest quality wines to their investors and they have subscription customers, right? So prediction accuracy is actually very important to them. So this is why it's important to, gather all that information beforehand, really write it up and make sure that we know the goal that we're going towards, right? Because now we have a way to objectively figure out, is my model good enough, right? And so I always stress that it's just so important not to skip this step. And it's the most time-consuming step as well. So you're talking to business owners and doing interviews and writing notes during this process. You're not doing any coding whatsoever. So people are generally surprised by that coming out of a master's in data science where you only focused on coding and algorithms, and now you're into this world of I have to produce documents and justify why I'm doing things. That's the first big shock for most people, but it's good. It's there for a reason. And then once you've done that, once you have successfully figured out what is my measure of success in this project, we have to do data exploration and data understanding. So we have to understand where it came from, what it looks like, and all the properties of our data. And so here I am using the Pandas library, so here PD, and I'm using the read CSV method from that package, and I'm reading in our data. So this is stored as wine quality. And then the great thing about Deepnote is if you just type this loaded data, I called it wine DF, and you hit play, you get really nice output. It summarizes the data set really nicely in a table for you. And it will count if you have categorical data like wine type here. We have white and red. So there you can already see I have 60% is white wine, about 40% is red. And then it will make a histogram for all of your numeric columns in your data, right? So you can do a lot of it's called exploratory data analysis, EDA, just by looking at this table. So we can see, for example, that our quality score here for all these wines ranges between 4 and 10, which is important to know. So they didn't produce any wine that was a quality of 1 or 0, which is good. And then the other important things that I always look for is I make sure to check out the range of each one of these columns and also the scale of each one of these columns. That's important to keep track of, right? So notice here I have alcohol content, which ranges from 8.4 to 14.9. And then I have this data here, the density of the wine. And this is on a drastically different scale. This ranges from 0.99 basically to 1, right? So very constricted range. So already, when I'm looking at data, I'm starting to see that, I might have to adjust for that different scale later on during a data pre-processing step. And you also want to be looking at things like, do I have missing data here? Do I have any outliers? Or do I have any skewness that I see, in my data? And this is why I really like these histograms here that summarize the numeric values, because you can clearly see that in this residual sugar here, the data is just very, very skewed, right? So this might be a problem. We might have a couple outliers here that are greater than 20 on this scale. So notice everything is kind of pushed towards the value of 0 here. So again, that might be something we have to take into consideration later to pre-process the data and get it ready. And just from experience, and you'll develop this as you fit more regression models as well. Generally, data that's very skewed isn't that great for linear regression, right? You have to really pre-process the data in a way to get better model performance in the end. All right, so that's kind of a high-level, quick way you can have a look at your data. And then the next step, the common step that I always suggest, is just to have a look at the summary statistics for each one of your numeric columns. And so the pandas package provides this great method, it's called describe, that will automatically calculate all of these summaries for every single numeric column in your data. And this is sort of strange syntax here, right? So I have these parentheses here on the outside, and then I start with a bunch of code being executed. And the reason I like to do that is because in Python, if you put anything surrounded by parentheses, you can separate the code and go to the new line. So you can go line by line. So it makes the code a little bit easier to read. And in Python, everything is called with methods, right? So we start off with this data frame. It's a pandas data frame that has all this data. And then I use the dot notation on that, and I call the describe method. And that's what's going to calculate everything for me. And then I call the round method, which is going to round everything to just 2 decimal places. So I don't have, 15 decimal places for all my summary statistics. And that's generally kind of the flow. At least when I write code, I like to have it line by line just so you can see what's going on and have it be very easy. So this is nice. You get a really nice summary of what's going on in your data. So each column here is listed, and then you can see how many observations there are, or rows. So that would be the count. And then we get the mean and the standard deviation values for everything. And then what's known as the percentile distribution. So you can go from the minimum to the maximum value and anything in between. So this is also really good just to look at. Again, one thing that should stick out here, if we didn't have these histograms here, where you could see the range right there in density, you would see it here, right? So here you would notice that, whoa, look at my density. It has a minimum of 0.99 and a maximum of 1. Wow, that's something I should probably look into. So this is really a good starting spot here. All right, so we have everything summarized. We've noted, things that we want to maybe look at, but it's always powerful to go ahead and plot these relationships, as well visually, because there's something to that. You might see some patterns that you can't necessarily just get from your summary statistics, right? And so this is where that package Seaborn is going to come in handy. So that package is loaded in our session as SNS. So this stands for that package. And I'm following the similar pattern as before. I'm doing a dot, and I'm calling a method of this package, and it's called pair plot. And this method, will take your data frame. So here it's winedf, my original data, something known as hue. So this is if you have any categorical data in your data frame that you want to separate the plot by, it'll give it different colors based on the values. And then this option corner is equal to true. And I'll talk about that in a little bit when we see what this visualization comes out to be, because I think that'll make more sense.
And does that function ignore all the other categorical variables that might be in a data set, or do you have to exclude them when running it?
Yeah, so it does ignore them automatically. It just plots the numeric ones. Yeah, which is nice. It's a nice feature. But you get a lot, just from this, couple lines of code here. It makes all of, they're known as scatter plots, pairwise scatter plots. So it looks at all combinations of pairs of columns in the data and produces a scatter plot for them. And notice that each one has its own particular color, and it stands for the wine type, either white or red. So here our white wine is the blue, and our red are the green points for every single one. Now, the reason I put this corner is equal to true here is because I want the upper half of this kind of matrix to be blank. Because by default, it will plot alcohol versus quality score, and then it will plot quality score versus alcohol on the other off-diagonal element. So it tends to be a little bit too much if you have a lot of variables. So this way you can kind of clear out a lot of that stuff. So as I mentioned before, we can have a good look at all these scatter plots, and we can already notice some differences, right? If I look at the bottom, the first column is quality score. And so that's what we're interested in predicting, right? So that's it's known as a target in machine learning. So those are our labels. And here we can look at, so what is the relationship between quality score and all of those other numeric columns in my data? And we can clearly see that the alcohol content, there seems to be a very strong, pretty good linear relationship between the two. So as quality increases, it seems like the alcohol level also increases, right? And there's a difference between the whites and the reds, right? They almost seem like they're separated on the alcohol content scale, right? So it seems like a lot of the white wines maybe tend to have a little bit more alcohol. And then on the diagonal, these are known as kernel density plots. And the way you can think about these is, so this first column here, quality score, if you make your way up to the top here, this is the kernel density plot for just that variable, quality score. And what it does is it separates it by wine type. So here we see that the white wine tends to be a little bit less on the quality score than our red wines, which are the green color, right? So it kind of like plots a distribution of what that quality score variable looks like just by itself. And the same thing goes for each one of these diagonal elements. So there's a lot we can learn just from looking at this. But these tend to be, if you have more than maybe even 5, 6 columns in your data, right? You definitely don't want to use pair plot and just spit out this massive scatter plot matrix, as it's called. It would be better to choose which variables you want to see. And so the great thing is that this Seaborn pair plot has that option. So it's called the vars option. And then all you have to do is pass a Python list with the names of those columns that you're interested in. So here I just wanted to look at just a subset of this data. And just so maybe these patterns are a little bit clearer and it's not so small. So it's easy to kind of see, the trends here, right? So it's a little easier to see that maybe one of the strongest predictors here is alcohol for my quality. I also see the total sulfur dioxide measurement. There seems to be a relationship there. It looks kind of like an inverse relationship. So there's a lot of great insight we can get from this. And we can also see, especially from the one at the top here, Something to watch out for when you're doing linear regression is if anybody has heard the term multicollinearity, and that's just a fancy word for if there are relationships between your predictor variables, or in machine learning, they're called feature variables. And we can clearly see that there are, right? So if we look at, for example, density with residual sugar, it looks like there's kind of a linear relationship, between those two. And that is something to watch out for. Some machine learning algorithms are not really affected by that, but linear regression is heavily affected by that because it really provides redundant information. If density and residual sugar have a relationship to each other, then you don't need both of them to make a prediction. You really just need one, because the other one is just providing kind of redundant information. So that's why I like these plots. It allows you to kind of see everything all in one and just look at these interesting patterns that emerge. And then another important thing to look at is correlation. And I'd like to talk a little bit about, just a reminder of what correlation is and what it exactly measures. But it measures the linear relationship between two numeric data sets, and it ranges from -1 to 1. And so Alex and I, we put together a couple, example plots to show you guys what these correlation values would look like if you were to see a scatter plot, of two numeric variables. And so if you have a negative correlation, so these are things that are close to -1, you would see, something like this pattern here, where I'm plotting fuel efficiency versus the weight of a car, right? So as a car gets heavier, the fuel efficiency decreases, and in a linear way in this plot. So you will commonly hear people say negative correlation, but sometimes they will also say an inverse relationship between the two. So that means when one value increases, the other variable decreases in a linear way, right? So as my car gets heavier, my fuel efficiency drops, right? So that's an inverse relationship between the two. And that's the trick I kind of use when I look at correlation values. If I see a negative, that means that there's a opposing effect kind of between the two. And then a positive correlation is the opposite of that one. So that is when one value increases, the other one increases, but in a linear fashion, if you have a correlation of 1. And so here we have another plot where we have exercise time in minutes. So the more you exercise, the longer you exercise, the more calories you are burning, right? So these go together. They increase or decrease the same way together. So that would be a positive correlation. And it's a nice, linear relationship here if it's close to 1. And then if you have a 0 correlation, it almost looks like there's just no particular pattern between these two variables. So here we have plotted on the x-axis, on the 0 correlation plot, we have average age of a household, and then we have paper plates used every month, right? So you can see from that data that there really isn't, a trend in any way. As you go from the average age of 40 up to 70, for example, the paper plate usage doesn't systematically increase or decrease in any way. It just kind of randomly, changes. So that kind of implies that there's no association between these two variables. So this is what you would expect if you had a correlation of 0. You would see this type of data. But Alex and I always like to warn everybody that a correlation of 0 does not mean that there is no relationship between two columns in your data. So that's a really important distinction, right? So here I have a plot of, and football season is coming up pretty soon, I think, right? When September or October, sometime in the next couple months. And I think Alex is excited about the Washington Commanders hopefully doing better. And I'm excited about the 49ers doing better.
Living in Europe now, football has a whole new meaning for us.
Oh, that's right. You get in trouble in Europe if you say football and you're not talking about soccer.
And the season never really seems to end. I don't fully understand which teams play in which leagues at which times.
Yeah, same here. But if we go back to football here, if I were to measure when I would take, let's say, Justin Tucker from the Baltimore Ravens. That guy's an awesome punter, right? So he picks up the ball and he punts it. And if I measure the time since the punt, and then I measure how high that football is, you will get this data here, this relationship. So it's the kind of curved parabola that you would see. If you remember, if you've ever taken physics before, this is just how a ball will go up and down in this parabolic shape. So if I take the correlation of that data set right there, I get 0, right? Because it increases linearly at the beginning and then it decreases linearly kind of in the end. So they cancel each other out. So that's just one thing to be aware of. So correlation of 0 does not mean that there is no relationship. You might have to look a little bit more closely at your data. So that's why visualization is really important.
And then the final qualification is the whole correlation does not equal causation, right? So just because we see the numeric relationship being either positive or negative in what looks like a meaningful way, we don't know what direction that relationship might be pushing each other.
Exactly. You don't know what is causing what, or if there is any causality whatsoever between those two. Yeah. The only way you can determine causality is you have to do a randomized trial. So if you've ever heard of A/B testing before, where you change something in one group and you don't change it in the other, and you compare them in an experiment, that's when you can kind of get at causality. But usually you can't see it from just observational data, out in the wild like this. So another important thing. All right. So how do we get correlations? We should have a look at our wine data and see what are they, And so again, here I am saving these into another data frame called wine core df. And I'm starting off with my wine data, and I'm calling the core method, and then I'm rounding everything just to 2 decimal places. So the nice thing about this method is that it will automatically just filter out only the numeric columns for you, and it's going to calculate all of the correlations between every single pair in your data. And if you're using Deepnote, the nice thing about this is you can look at, for example, quality score here. That's what we're interested in predicting. And we are really interested in what is highly correlated with that quality score. That's going to be the most important column in your data to use as a predictor. So you can easily sort these in Deepnote and just, kind of have a look, right? And using those rules that kind of I talked about before, total sulfur dioxide. So we see a negative 0.54. So that's, pretty good negative correlation. So I already know just from this number that these two have an inverse relationship with each other, right? If I increase my sulfur, I'm going to decrease my quality, right? So always the opposite of the two. And then if I go ahead and sort it the other way around, I can see that alcohol and citric acid are positively correlated with my quality score. So the more alcohol, the better quality, right? That sounds like a good game plan to me. That's always good. All right, and you can do that for every single combination here. So I usually focus on just the target column, the thing I'm trying to predict, and I look at all those correlations first. And then I will look at, are there any other correlations between the predictors themselves that I should watch out for, right? So you can sort each one of these as well. And here we see, for example, that we have a pretty strong inverse relationship between alcohol and density. So if you're doing linear regression modeling, that is something that we'll have to consider as we do more data preparation steps a little bit later in the series. All right, so this is also helpful to get started. And if you want to visualize these, because I know for many people, just looking at this table of numbers can just be a little overwhelming. And it's hard to figure out what the patterns are. There's another useful method in the Seaborn package. It's the heat map. And all you have to do is you have to pass this correlation data frame that we created to it. And then I just like to use these parameters here as a default, because I think it just makes it easy to distinguish between all these different correlations. So here you basically get that same exact correlation data frame, but now you have the color associated with it. So anything that's really, really blue is a positive relationship, right? Anything that's really, really red is a negative correlation with each other. So here things kind of stick out more easily for some people, right? So you can look at maybe just the first column with quality score, and you can quickly see that positives relationship, right? Alcohol, a negative relationship with sulfur and residual sugar. So that really comes out nice and clear. And you can see the correlations between the predictor variables themselves as well a little bit more easily here. So just another function here just to make your life a little easier.
David, someone has a question about negative versus positive correlations and their influence on a linear regression model. Like, is it better to have a very high positive correlation versus a negative one?
No. So the direction doesn't really matter. If you have something that is very negatively correlated, it's still going to be a good predictor. So that's not going to affect your prediction quality. The only thing that will affect your prediction quality is the closer you get to zero on correlations, right? So if you have just a zero correlation between quality score and everything else, that means that there really isn't that much there to predict, right? Mm-hmm. So that's something you should look out for. So really large negative numbers and really large positive numbers both can be used for prediction, right? It's going to be really good, most likely, but just watch out for the zero. But I say that, with a grain of salt, because zero doesn't mean no relationship, just like we showed before. So it requires a little bit more digging. So there might be a way to predict, but generally zero is what you want to avoid. Yeah, that's a good question. All right, and now we get to the data preparation, right? So we've looked at our business problem, we've explored our data, and now we got to get it ready for our machine learning algorithm. So we're going to be using Scikit-learn. So the one thing is that's almost universal for all the models in Scikit-learn is that they require a numeric feature matrix as input. So they require numbers to make predictions. So all the data input has to be numbers. So we can't have things like text or categorical data. So our column in our data that says white and red for the wine type, all right, that would be a problem if we used it as is. So the things you're doing with data preparation is in this image here. So you're taking the raw data you have and you're applying all of these transformations. And sometimes you're using different technology to do it, maybe Python, SQL, Spark, if you've ever heard of it. But it gets you to that final numeric data matrix, which Scikit-learn expects for all of its models, model training. And you end up with a target column, which is what you are trying to predict. So this is the supervised learning case. And then you have the other columns in Scikit-learn are known as features. So these are attributes that you're using to find the patterns and make that prediction, right? So this is just a nice visual, taking some customer data up at the top that's really kind of messy, has a lot of text. It has people's LinkedIn profiles, how much they spent, right? And then you go down, everything is turned into numbers. So if this, is a little bit confusing, that's okay, because this webinar series, we have a whole webinar dedicated just to how do you go from this raw input to that numeric data matrix. We're going to go through all of those functions that Scikit-learn has. All right, so we aren't going to worry about that in this introductory lesson. We are just going to use alcohol content, and we're going to predict the quality of wine using linear regression. So we don't really have to prepare anything. Everything is already in numeric format, and we're good to go. And just as a quick recap, so linear regression, right? We are predicting something. It's written as a y in general, and using a linear function. So we have two parameters in this model, a beta 0 and a beta 1. And then we have a little x. So that is what you're using to predict. So for us, it would be alcohol in this example. And our y is our quality score, right? So we're just fitting a line to the data. And the beta 0 is, what we're going to get as a prediction when x is 0. So when alcohol is 0 in our case, what's going to be our predicted quality? So hopefully it's close to 0, because that doesn't sound like it'd be very good alcohol, but who knows? And then your beta 1 is the slope of the line. So if you remember rise over run formula, so I have this triangle here in this image, but the important aspect of that is just remember that the slope of the line can give you, if I increase my x value by 1, what happens to my y value, right? So a 1 unit increase in x gives me what change in my y in the thing I'm predicting. So that's a nice interpretation. All right, so let's get into the next part. Now we're in the modeling phase of data science. So there's one step we have to take. It's known as data resampling or cross-validation, if you've ever heard of that term before. We have to take our original data and we have to split it into 2 sets. So a training set and then a test set. And the training set is what we're going to use to fit our model to get those parameters, that beta 0, beta 1. And then we're going to have our trained model. And then we're going to use that to make predictions on the test data to see how well it does. So that's the typical workflow when you're fitting machine learning models. Okay.
And I think this is the big difference, what we talked about earlier, that a lot of people have done regressions, whether it's in statistics courses or econometrics courses. This is where the process probably feels a little bit different for those of you who did that, years ago when you first learned.
Yes, yeah. There wasn't as much emphasis on splitting, but I'll show you why this is important after we actually fit the model. There's a very important reason why we do this, and I'll mention it again. So there's a helper function that we imported from Scikit-learn. It's called train test split. And it will take the first argument is what are your predictors or features. And then here I'm saying the alcohol column from my wine data. And here it's important, I want to call out to use 2 brackets when you are subsetting this data just to maintain the dimension. And if that's a little confusing right now, again, that's okay. In following series, we'll go into the details. And then the second argument is your target. So this is what are you trying to predict? So here I'm using a single bracket, extracting quality score, and then extracting the actual values from it. And again, I'll talk a little bit more as we go into feature engineering next time. And then here I specify I want 75% of my data to be in training, and then the rest in test. And random state is just a random seed so that you can reproduce this split again when you run it, maybe tomorrow. That's also important. So this thing returns 4 things: X train, X test, Y train, and Y test. So it splits our data into these 2 things. And if we want to see how many rows there are, you use the shape method on them. So we can see that our X train has 1 column, which is the alcohol column, and just over 1,200 randomly selected rows. And then same thing for our Y train here, right? So here we have, and these should match the 12,000 rows between the 2. So we have ones for training and test. So now we can get to fitting this model. And most first-time users of Scikit-learn will be pleasantly surprised that this is pretty easy to do. Most models in Scikit-learn follow a similar pattern. So the first thing we have to do is we have to instantiate a linear regression object. So this is where we are using this method here, this function here, this linear regression. So we think about just initializing a linear regression model that's empty for now. So it doesn't have data yet. It's not fit yet with all the parameters, but I'm calling this wine LM. And now I can use it. So I have these 2 important methods called fit and predict that we'll be using on this wine LM. And all we have to do is use this fit method on this wine LM, and I pass it my X train and my Y train, and then we're ready to go. It estimates those model parameters. And so here, I left something, a blank code cell here, just so I can show you. Once you fit a model and you hit the dot button, these are all the things that are available to you after it's been fit. So now if I do maybe the coefficients, it's going to print out what it estimated to be the beta 1, right? So after you do the fit, all of these things get kind of populated in your linear regression object. So here, just to show you, we can access the intercept and coefficient attributes, but this is the line we got from our linear regression model that we fit on our training data, right? So our beta 0 is 0.48. So that means if my alcohol is 0, my predicted quality is only close to 0, basically, which kind of makes sense. And then if I increase alcohol by 1 point, right? If I increase it by 1, my quality goes up by 0.64. So that's a nice interpretation as well. But this is the line we get.
And I think it's probably good to point out that no matter what data you put into it, you're going to get an equation coming out of it. And that doesn't mean that the equation is good. It can be used for sure. But as David is going to walk you through when he looks at the predictions and then evaluating how successful it is, just because you get an equation from it doesn't mean that it is a good model that you're going to be able to use.
Yes, yeah. And it's very important to get into this evaluation step here. Now, this next code chunk will show you how to get model predictions using this line that we fit, right? So we can use the predict method on our wine LM that's been trained. And I've done that here with my training and my test data. So I did wine LM and I did predict, and then I passed it the training data and then the test data. So these are my X's, right? And then I created a pandas data frame and put it all together so we can see what we get, right? So we have a quality score. So this is my Y test. So this is the truth. These are my real quality scores. And then using my model, these are my predicted quality scores. So I got these with the predict method. And you can see that, you know, it's pretty good, but we're off by about 1 point, right, roughly, between each one of these quality estimates. But overall, you know, not a terrible model. But it's really important to look at the performance metrics just to get a better sense of how this is performing. So there are two that I want to talk about today, and I'm sure most of you have heard of these two. So the first one is called R-squared. And this can be used for any regression model, not just linear, but it's the squared correlation between the actual values, the truth, right, in your data, and then what your model predicts. And the way that this can be calculated is you can use the score method. So by default, you get this R-squared metric back. So here I'm using my wine LM again, and I'm scoring it on my training data. So you pass your X and then your Y. And I get about 0.43 R-squared. So just this ranges from 0 to 1. So this is kind of a not so great model. 1 would be the best. 0 is just absolute worst. And then notice what happens here when I do the same thing on my test data. I get something worse than I did on my training data. So that's why it's very important to split your data up before, because any machine learning model is going to kind of do a much better job on the data set that it was trained on. But you need to have a way to have some data you've held back during the process to test how well it generalizes to new data sets, because ultimately that's all that matters for your machine learning models, is how they perform on new data, not on what you trained it on, right? So,
and David, take that 0.3684 number.
Mm-hmm.
I've heard before people say from that, 37% of the variation in quality is explained by our model. Is that an accurate way of describing it in human terms?
Yes, but that usually only works for linear regression specifically, like that definition of R-squared. So when you're doing linear regression, you can say that, where about 37% of what's going on in my Y's I could explain with this X, right? But not necessarily if you're fitting a decision tree regression or something along those lines. So that's why I like this more general definition, is it's just a squared correlation between those two quantities. And that applies to all regression models.
Right. I'm just thinking reporting back to the business units that you're working with.
Yes. Yeah. Well, I mean, I'll show you in a little bit. I usually never report the R squared. I do a graphic of this.
Gotcha.
And I know we're running out of time, but we're almost done. So maybe we can go a little bit over a couple.
It's okay. Take your time. No real pressure.
And then so here we have this R squared. So this is good, but we still need to visualize kind of what's going on here, right? I don't like to look at just the R squared number as just a number, and I'll show you that in a little bit. Another common metric is root mean squared error. And just roughly speaking, a good definition of that is that the RMSE, it represents your average prediction error of your regression model, right? So kind of on average, by how much are you off usually in your predictions? And the way we can calculate this is we use the mean squared error function from Scikit-learn, and then we pass the truth, which is y train. That's the first argument, y true. And then we pass predictions. So here I'm doing y_lm dot predict x train. So I'm getting those predictions for the training data set. And I select squared is equal to false. So this will give me my RMSE, and it's 0.87 roughly, right? So this is on my training data. And so here, my predictions are off, kind of on average by about 0.87 or so. And we saw that earlier when we looked at our actual training data, right? If I go up here, the difference between these two kind of seems to be, about 1 or so, 1-ish, either in the positive or the negative direction. So that's what this number is giving you. And this is exactly the number we need for evaluating our model in this case, because remember, the business told us it's got to be within 0.5, right? So now we clearly know this model is not good enough on the training data. And the same thing happens here when I use the same function, but I'm using the test data in this case. So I get something, similar, 0.84, basically the same error, right? So since we have that success metric, we know this model not good enough. Right, so we're going to have to work some other type of magic and maybe use more columns to see if we can get a better model. So I'm trying to hook you guys to join us next time because that's what we're doing. All right, and then one last thing I like to do with this RMSE. So this version of it depends on the units of what you're predicting. So someone, if they looked at that 0.84, they would have to know that your quality score is on a scale of 1 to 10 for that to really make sense to them, right? But another way is you can simply take that RMSE value that you got and divide it by the average of the actual values that you have in your data set. So here I did that for the test data set. So here I get my RMSE at the top, same thing, as we had up top. And then I'm using the mean function from NumPy, and I pass the y_test values. So those are the true values. And now this turns into a proportion. And now you can say that my model has about 12% prediction error. So this doesn't matter what the scale is of your output or of your target. It's just you've got 12% error. And so usually people can understand that regardless of scale. All right, and then the last section here is going back to R squared a little bit and why it's important to visualize it, to see where it came from and how we got that number. So here I'm using pandas again to create a data frame, and I'm calling it training results. So I'm creating a quality score, which is just my Y train. Those are my true values. And I'm getting my predicted values from my model that I used predict on before for my linear regression object. And then here I'm calculating the prediction error. So I'm taking my predictions that I have and I'm subtracting the truth, which is Y train. Those are the real values. So when I create this, you can really see kind of what's going on here, right? So my prediction was a little low for the first bottle of wine here, very low for the fourth one, at like a -1 score, right? So you can use this data frame to explore where all these errors came from and why they're happening. That's really important to do. but a kind of industry accepted plot for all regression models is called the predicted versus actual plot. And this gives you all the information you would want to kind of diagnose your errors or your model errors. And luckily, we can use Seaborn for this as well. So this time we're using LMplot. And now I'm using this data frame that I created here, training results, that has the truth and my predictions. And so here I'm saying on my X, give me the actual quality score. On my Y, plot the predictions, use this training results data frame, and then fit, it's called the identity line to it. And I'll talk a little bit about that in a second here. So this is what we get. So this is kind of the manual way to do it if you want to make one of these plots yourself. You have to add all these extra parameters to it. You have to add the line Y equals X. But I won't talk too much about that because there's an easier way to do it in the code below. But just wanted to show you for those that are interested in making it yourself. But this red line is the line Y is equal to X. So that means that my predictions always equal what the truth is in my data, right? So I have a perfect model. So if all of these points were exactly on that red line, that represents an R squared of exactly 1, right? Everything is a 1-to-1 mapping. And so we got an R squared of about, I think, 0.42 on the training data. And so this is where you can see how we got that, right? Where did we not do so well, right? And just looking at this data, if I look at my quality score of a 4 or a 5 or even a 6, a true quality score, my model is over predicting all of those, right? It's predicting a 6 or a 7 for all of those. And you can clearly see that happening on the kind of left side of this plot here. So this is a really important, plot to look at just to diagnose what's going on. I can already tell my model performance is not very good if it's less than 6, the truth, or if it's greater than 8, it's having trouble there, right? And it really kind of comes out here in this plot. So like I mentioned before, this is the kind of hard way to do it if you're going to make it yourself. Luckily, from Yellowbrick, this extra package in Python makes this really easy for you. So all you have to do here is use this function here, prediction error. You pass in your trained model, which is my wine LM. And then here you specify is fitted to be true because we already trained it on our training data. And then we use the score method on this object that I created, and I pass it my test data. So X test and Y test, and then I use the show method, and it's going to create what we did here, the kind of difficult long way, right? Because we had to create this training data frame here and then pass it to Seaborn and make the plot. This does it without having to do those steps. And you can clearly see, the same plot on our test data here, right? So here we can see on my Y-axis, you see a Y hat there. That means your predicted values. And then a Y is the truth on your X-axis. And our R squared is 0.37, right? And this is kind of how we got it. And same problems in the test. My model over predicts for true values less than 6. And then it under predicts for values that really are 8 or more, right? So I have this problem in my model. And if you wanted to explore your errors, so these are called residuals in linear regression, you could use this function here from Yellowbrick. It's called residuals plot. And it's the same methodology as before. You simply pass your trained model into this, you score it on either the training or the test, whichever one you'd like, and then you call the show method. And it's going to make a nice plot of just your errors of your model. So here you could have a look on your X-axis. This is what your model predicts. And then residual stands for the error, right? So that's how much it was off by from the truth. And so the one thing you want to look here in these residual plots is, do you see any kind of systematic patterns in your errors, right? Do you see maybe a curve in there? So maybe that means that a linear model isn't the best thing to model your data. is it only making errors in one particular region or not, or another, right? So these are the things you should be looking for when you're evaluating things. But
so David, what you would like to see on that right-hand histogram is pretty much a normal distribution.
yeah, I mean, you do want it to be relatively symmetric, but the important thing is you want ideally the bulk of the data to be close to zero there, right? And not like a wide distribution. That just, so for us, the data, it's kind of a wide distribution. You can see where we got an RMSE value of 0.8 something, right? And so most of that residual data lands between 1 and -1 for that reason, right? So you want it to just be as close to zero as possible. I mean, and that's what you want to look for. But if you have any skewness there, right, that would be a problem too.
Yeah, which is also, I mean, we see it again with the relatively low R-squared value. And my guess is next time when we regroup, we're going to go through and do some things to this data set to try to improve the model.
Absolutely, yes. Because what this is telling me is not necessarily that it's a bad model, it's just that using only alcohol is not great for predicting really poor quality or really great quality. It does okay in the mid-range. So what if we add something else? What if we add pH or density or all these other attributes we have? It might be better, right? So this is only a beginning point in this experimentation phase. So it's very iterative every time you're fitting models.
Yeah, that's great. And I think now is a good time to wrap up this first workshop. Next month, we're going to come back to the data set, add some new variables into this, start controlling some of the issues that we found in the underlying data set. I've got one question coming in on, is this recording going to be available? So if you registered via Zoom, we're going to send you an email. We're going to give you a link to the video and all of the code and the data sets as well. If you are joining us on YouTube, I'm going to put a link in actually the channel, both for the chat in Zoom and in YouTube, the link to our website where we will also store the material for this session. And David, actually, if you could share your screen one more time for us to sign off with.
Oh, sure.
I just want to ask you to pull something up. And that was great. That was a really sort of clear way to sort of start setting up a linear regression model. We're going to meet a month from today, so on the first Saturday in August. But Dave, if you go to dataquery.com, I just want to show everybody that is joining us the other resources they can look at over the next month if they want to keep going deep on this. So the website that we put together has at this point, nearly 2,500 data science courses. Just type regression into the search here and see what comes up. And you can see, we've got 90 specific courses that are coming up right now on a whole different amount of regression techniques within the context of machine learning. For some of them, you can filter it by free and the level and the length, really just to get a sense on, what might be working for you. So what we hope is in the next, including free textbooks, which is actually one of the most popular sections on the site for sure right now. So in the next month, as you are signing up, or if you want to continue the workshop sequence with us, but you want to get a little bit extra help, go to some of these courses. Also, feel free to reach out to us with questions or other techniques or concerns that you might have from this type of material, and we'll work it into either a direct response to you or into the next workshop that we put on. I think it's the 5th of August. With that, thanks for joining us today. David, thank you so much for your time and your clear explanations around how to set up your first regression models in the machine learning context within Python. Obviously today, the tools that are out there, the free tools that are out there, the free learning material that is out there is incredible. And I think the most effective way that you can start to use these techniques yourself is to get a data set you really care about, that you know a little bit, and then start playing around, start putting some of these on those data sets, and then hopefully coming up with some kind of predictions that can help you out in some way.
Yes, yeah, definitely. And feel free, if you have a data set you're interested in and you are in our Deepnote, environment, you can always upload the data into that and then use the code we put together. And just that's the way you learn, I think, is try to fit it on your data, see what results you get, and kind of play around with it. And don't be scared, right? Just go ahead, just get in there and start doing it. And you'll be a pro before you know it.
Definitely. All right. Thanks once again to everybody who joined both on YouTube and in Zoom. Feel free to reach out with any questions. You can find our contact information up on dataquery.com. We'll see you next month. And thanks again. Thanks, David.
All right, bye. Bye, everyone.